Lesson 68, we're going to play with something called exponential functions. Now, why are they called exponential functions? Well, they're functions, which usually means you're going to plug x in, right? Look where the x gets plugged into. It gets plugged into an exponent. Get it? The x is an exponent, or at least it's in an exponent. That's what we mean by exponential functions. Okay, so what do they look like? Well, here's a nice example, 2 to the x. Now, I always like exponential functions for this reason. You can bang out real nice graphs of them if you just plug in these 5 values for x. -2, -1, 0, 1, and 2. It's great. I'll start at the bottom of the list here. If I were to plug in x equals 2, 2 to the 2, well, that's 4. If I were to plug in x equals 1, I'd have 2 to the 1, well, that's 2. If I were to plug in 2 to the 0, remember what you get? You get 1. How about this one? Do you remember what you get when you go 2 to the -1 power? It's like 2 to the 1 power, but with an added twist. The negative on the exponent means flip me over, it's a 1/2. And then 2 to the -2, there's a 2-part exponent. You are supposed to square the 2, but you're also supposed to flip it over, so you get a 1/4. Okay, cool. Nifty. Now, let's just graph that real quick. -2, 1/4. Let's see, that would be something like here. Come on, you. That would be something like here. -1, 1/2 is about there. 0, 1 is about there. 1, 2 is about there. 2, 4 is about there. Notice it just keeps rising faster and faster. So I'm going to call this 2 to the x. And when you go back this way, imagine, well, you can see the pattern here, 1/2, 1/4. It's going to be an 1/8, and then it's going to be a 1/16, and so on. It's just going to shrink closer and closer towards the x-axis. In fact, the x-axis is a nice horizontal asymptote. So when you're drawing these things, you really should draw the asymptote, because that's an important piece of information. It's like, gee, is that thing approaching the x-axis? And when you put the dashed lines there, the answer is, yeah, it really is. It's approaching without touching the x-axis. You also put the arrowheads on there to say, yes, it's continuing forever in this direction. Okay, so there's a nice function, 2 to the x. Kind of cool, right? By the way, this is kind of related to what we were doing yesterday, right? Remember when we were doing geometric sequences? And we said, you know, you'll have some kind of a common ratio, like maybe r equals 2. You would keep doubling every step of the way. Well, look what's happening here. Here I'm at 1. If I take 1 step to the right, I double to 2. If I take 1 step to the right, I double to 4. If I take 1 step to the right, I'll double to 8. And so this is kind of the same thing. It's not exactly the same thing. There's a distinction we'll need to make later. But it's kind of the same thing. It's kind of related to that whole geometric growth idea, except we call it exponential growth. But it certainly looks similar, right? Again, there's a distinction that we'll have to make at some point, but not right now. Let's look at another one. Let's look at 3 to the x. Well, what I was saying before is still true. You want to graph a nice basic exponential function? Plug in these 5 values for x. So if you plug in a -2, 3 to the -2 power, you would square it, you would flip it, you would get 1/9. 3 to the -1 power, you would just flip it, get a 1/3. 3 to the 0 is 1, 3 to the 1 is 3, 3 squared is 9. So if you were to plot this one, notice you're going through this same point, 0, 1. Okay, but then you're going through 1, 3. And then you're going through 2, 9. It's way the heck up there. Okay, at -1 we're at not a half, we're at about a third. And then at -2 we're at like a 9th. So what's happening is over here on the left side, it's below 2 to the x. It sort of hugs the x-axis faster or something. But over here on the right side, when x is positive, it's climbing way faster. And why is it climbing way faster? Because this is like a tripling function. I'm at y equals 1, okay? Now I'm at 3. Then I'm at 9, right? I keep tripling. It's kind of like the geometric growth with an R of 3. Kind of. Pretty much. Okay, that's what 3 to the x is. Now, before I do this other one, we've got this new number to look at, e. But before I do that one, what's happening here? Get the green out of there, get the green out of there, get the green out of there. Okay, before I look at that one, I want to come down to the bottom where it says interesting thing. You see that 2 to the x and that 3 to the x? Don't they look like they're almost the same thing, just a little, I don't know, stretched or something? Like one is just a kind of a stretched version of the other? Turns out that's exactly right. So here's the interesting thing. If you were to write this, 2 to the x, that would be the same thing as 3 to the, what do I got here? 0.63093x. Those give you the same graph, or almost perfectly the same graph. I can prove that to you real quick. If you just take 2 to the power of take 3 to the power of 0.63093, you will get 2. So it has to be true. So if you raise this to the x and you raise that to the x, it should come out exactly the same, right? But think back to our transformations days, lessons 57, 58, 59, when we did stretches and compressions in particular. Remember that if you were to take a function and you were to put some kind of a fraction in front of the x, that was a vertical stretch by a factor of b. So this is like a fraction because it's less than 1. This is a vertical, what am I saying? Vertical? Horizontal. Sorry, horizontal. Fix that. This is a horizontal stretch. In other words, 3 to the x is this thing. If you were to do a horizontal stretch by a factor of whatever the heck that is, 1 over 0.63, whatever that is, you would actually end up on top of 2 to the x. So if you stretch this point by the same factor, you'll end up on 2 to the x. If you stretch this point by the same factor, you'll end up on 2 to the x. If you stretch this point by the same factor, you'll end up on 2 to the x, and so on. So these things really are related. They are related by straightforward horizontal stretches. Any exponential function, 5 to the x, 9 to the x, whatever you want, they're all related to each other by a simple horizontal stretch. That's kind of cool. Now I got to get these arrows out of the way to bother me. Okay. Put you back. You didn't bother me. Okay, cool. Okay, so let's look at this e to the x. And the reason we're looking at e to the x is because e is one of those numbers that comes up quite a lot, especially when you get beyond college algebra. It's going to show up a ton in any kind of calculus context. What is e? E is approximately equal to 2.718. Approximately. 2.718281828, if you want to be a little more accurate. We don't have to be. But 2.718 is a good approximation for E. It's called Euler's number, and the word Euler begins with an E, believe it or not. So Euler was some Swiss guy's last name, and he had a lot to do with this number, I guess. Probably discovered it or something. And so we call it Euler's number. So if you want to do a graph of e to the x, you're going to want to do the same thing. Put in -2, -1, 0, 1, and 2 for x. And then you're going to want to get out your decimal. Get out your calculator and figure these things out. Well, e to the 0 is going to be 1. I know that. E to the 1 is going to be e. I know that. Let me just approximate it as 2.72. E to the 2 power. So go on, calculator. 2.71828 squared is just about 7.39. E to the -1, otherwise known as 1 divided by e, gives me about 0.37. 2 decimal places is plenty if all you're doing is making a graph. And then e squared but flipped, so that's 1 divided by e squared, basically. Is about 0.14 if I go to 2 decimal places. Okay, so let's try to graph this. When I'm at x equals 2, I'm at, well, when x is equal to 1, I'm at 2.72. So notice that's about here someplace. When x is 0, I'm at 1, that same point again. When x is -1, I'm at 0.37. So that was 0.33, so 0.37 is about here. And the point I want to make is it's basically in between the two. Why is it in between the two? Because e itself is in between 2 and 3. So if e is about 2.7, you expect the graph of e to the x to be somewhere between 2 to the x and 3 to the x. So anyway, e is a number we're going to start seeing a lot of. And just try to remember it's like a number, 2.718. It's kind of like pi. It's one of those numbers that goes on forever without any patterns. Cool. So in passing, I call these 5... Whoa, man. I call these 5 points -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4. I call those the 5 amigos. Because they're 5 friendly points. If you generate those points real quick, you can graph 2 to the x real well. And then for 3 to the x, you have, of course, a different set of 5 amigos. But those 5 points, where you plug in x equals -2, -1, 0, 1, and 2, those are the points that I'm referring to when I say the 5 amigos. Like on the next page. So it says here, what do we got? We're going to practice with our exponential functions a little bit and graphing them some more. Graph f of x equals, whoa, it's a little bit fancier, by applying transformations to the 5 amigos and the asymptote. Yeah, all of these have the same asymptote, by the way. Okay. In other words, we want to graph this function. Now I'm going to start by making a graph of 3 to the x. That would be called the parent function, or you might think of it as the stripped down to its bare bones function. In other words, don't worry about the negative. Don't worry about adding 2. Just don't even think about that. Just add it. In the beginning, this used to be a 3 to the x. So just think about those 5 points. Those are the 5 points we want. So, but I'm going to do the old -2, -1, 0, 1, and 2, because those are how I get my 5 amigos. 3 to the -2, again, that's 1/9. 3 to the -1 is 1/3. 3 to the 0 is 1. 3 to the 1 is 3. 3 to the 2 is 9. Cool. Now, apply transformations. In other words, read off of this thing what is happening. There's 2 different changes that are being made here. So we're applying the old, whoops, maybe I should say this. How do we get the 2 there? We go like this. We turn x into an x plus 2. Okay, that's how you can read it. Now, do you remember what this does when you replace x with an x plus 2? That is a shift to the left by 2. So our graph is going to be shift to the left by 2. Now, what about this negative in front? Now, that's in front of the whole function. Right, so that's another change we're doing. Putting a negative in front of the whole function. What does that do? That reflects it over the x-axis, in other words, up and down. So what we're going to do then is we're going to take these 5 points, and each point we're going to move it to the left, and we're going to reflect it. And then we'll end up with our nice graph. So maybe what I'll do is I'll get some gray out. I'll graph these 5 points so it's easier to follow what I'm doing here. So -2, 1/9 is about there. -1, 1/3 is about there. 0, 1, 1, 3, and of course 2, 9 is off the charts. But anyway, we're starting with something like this. That's what we're starting with, and remember there's an asymptote there. Now, let's get the real function going. Remember my 2 moves. Left 2, reflect over the x. I do both of those moves for every single point. This point, I go left 2, puts me over to there, and then I reflect over the x-axis, puts me over to here. So that point ends up down here. This point, I'm going to go left 2, and then I'm going to reflect over the x-axis, puts me here. Maybe one more point. This point, I go left 2, I reflect over the x-axis, puts me here. Notice if you did that with the horizontal, if you did that with the asymptote, you took these gray dashes and you shifted them left 2, and then you don't have, reflecting them, they don't go anywhere, they're on the x-axis. You end up with the exact same asymptote, so I'll make a nice purple asymptote here. And here's my new function. it just kind of looks like it got a little moved over, I guess, and reflected. And it'll cross this axis. There's no asymptotes here or anything. There's no vertical asymptote. So it's going something like that. So there's our graph function. So that's what I mean by applying transformations. So to make a nice graph, you always want to plug in -2, -1, 0, 1, and 2, but you want to plug it into the basic, the parent function, the non-transformed function, the original function. Then follow those points as they get transformed. See where they end up. That'll give you a really nice graph. Oh, let's see. Let's do that again. How many examples have I got here? Oop, okay. One more of these, and then I got something else. One more of these examples. So let's get out the blue here. So the first thing you do is you look at this and you say, what a mess. And the next thing you do is you say, well, that used to be just y equals 2 to the x. That's what it started its life as. So let's get my 5 amigos going for y equals 2 to the x. -2, -1, 0, 1, and 2. 2 to the -2 power is a fourth. 2 to the -1 power is a half. 2 to the 0, 1, 2 to the 1, 2, 2 to the 2, 4. There's my 5 amigos. And I think, what the heck, I'll graph them in gray right now. In gray. I said gray. Okay, so -2, 1/4 is about there. -1, 1/2, 0, 1, 1, 2, 2, 4. This would be an asymptote. Ask them. It's an asymptote. Just ask them. Anyway, it's going something like this. So there's our original function, our 2 to the x function. But we're going to make some changes. What are we going to do? We're going to, what color did I use? Probably this color. We're going to, well, you have to look at this thing and say, there's different stuff going on here. One thing that's going on is we're adding 1 to the whole thing, right? Because 2 to the x lives over here, but then we're adding 1. So that's one of the changes we're going to make. We're going to add 1 to the function. Remember what that does. That means the function's going to go up by 1. What else are we doing? Well, to get this 1 over here, I would have to take the x and replace it with an x plus 1. Because x plus 1 and 1 plus x are the same. So that means I'm replacing the x with an x plus 1. Do you recognize what that does? That's going to be a left by 1. Okay, cool. So now I'm at here, and now I just got to get that x to be negative. So take the x and make it negative. Remember what that does? That would be a reflection across the y-axis, which means left-right, like this. So those are the 3 things I want to do to these points and to these asymptotes. Do all 3 things. So let's start. I'm going to start with this point. Go up by 1. Go left by 1. And now reflect over the y-axis. I end up over here. Like that. Take the point that used to be here. Go up 1, go left 1, and now reflect over the axis. You end up here. Interesting. Let's take this point. Go up 1, go left 1, now reflect over the y-axis, so you bounce over to here. Interesting. Let's just take this point. Up 1. This is at a half, right? So up 1, left 1, and now bounce over to the other side. Let's do it for the asymptote. You take these gray dashed lines. You go up 1. Now they're up here. Going left 1 doesn't do anything. Reflecting back and forth left right doesn't do anything. So my new asymptote is actually up here now. So my new function has its asymptote moved up to here. I've got those nice 4 points. Give me a really good idea what's happening here. So I can kind of draw my line. Don't forget your arrowheads. Don't forget your asymptote. And so on. So that's how you can bang out a graph of that funky looking thing. Start with the basic function, apply your transformations, and bada boom, bada bing, you'll have a really nice looking graph. Okay, this is the last page here. Now I'm going to show you something kind of cool. Going back to the first page, I was saying when we graphed these things, I was saying, hey, isn't that kind of like geometric growth? Because you keep multiplying by something over and over and over. Yeah, it is a lot like geometric growth. You might expect we could use a geometric growth formula. Well, we almost kind of can. What am I talking about here? Okay, a certain lunar crater sustains a population of moonsters. The population is 40 now, and it's going to keep doubling every 6 months. What will be the population in 10 months? Okay, it's 40 now, and it's going to keep doubling. So if we modeled this as a geometric sequence, we'd say, well, it's 40, and then it'll double to 80, and then it'll double to 160, and then it'll double to 320, and so on. So it is a geometric sequence in that sense. But how long does it take to get from 40 to 80? See, this is a new factor here. It's like, well, it takes 6 months to do that. And it'll take another 6 months to double again. And it'll take another 6 months to double it again. So see, time is involved here, right? It's not just that we have a list of numbers. I mean, yes, the R is equal to 2, that's for sure. But it takes 6 months to get there. It takes 6 months to make a jump, you know. And the question is, what will be the population in 10 months? What do you mean 10 months? Where's 10 months? 10 months is, well, it's not quite that far, right? That would be 12 months. So it's got to be something kind of like, I don't know, 120, 130, something like that. You know, 10 months is, you have to kind of, you know, guess a little bit, okay? This is the big difference between geometric and exponential functions. If you model this as exponential, here's what you can do. You can say the population is, or y is, maybe I'll just use y. People are always comfortable with y. Y is, start at 40, keep doubling. Now remember, for a geometric, we would do this n minus 1 thing, but that's not what we want to do. We've got time here. What we want is, we want it to double when 6 months have gone by. So take the time and divide it by 6. And notice that when t equals 6 months, the exponent is 1, so it's times 2 to the 1. Man, these things. Go away, go away, go away, go away, go away. How do you get it to go away? I don't know how you get it to go away. Go away. I'm trying. Sheesh. Everything's got to have a shortcut button. Anyway, when t equals 12 months, that means the exponent is 2, which means we've got times 2 squared, right? It's working. That works pretty good. And what's nice about it is you can set t equal to any number of months you want. You don't have to land on 6 months, 12 months, and so on. You can set it equal to anything you want. So I love this. I just love this. So this is put the 2 here because it doubles every 6 months. That's how you can put these formulas together. Start at 40. Start at 40. It's almost like you do it this way. Start at 40, keep doubling every 6 months. You can build your equation just like that. What do you say we solve the thing, huh? Yeah. So if I put in 10, well, you're going to want a calculator for that. We're going to have a nice answer here. So 10 divided by 6 is, boom. 2 raised to that power is, boom. Multiply that by 40, boom. And I'm getting 120, just about 127.0. So I was thinking 130 or so. Turns out I was kind of close. 127. Ain't that nifty? Ain't that nifty? What do you think of this one? Pause and think for a second how you might do this one. Here's how you might do this one. Biffanium 238. Now the 238 is not something we're going to plug into any formula. It's just the name of the element, Biffanium 238. Anyway, it has a half-life of 400 years. What does that mean? It means the amount keeps cutting in half every 400 years. So if you store 100 kilograms of this stuff, okay. So you're going to keep cutting it in half, right? Keep cutting it in half, keep cutting it in half, keep cutting it in half. This is what the sequence is. And it's, what does it say, every 400 years? So it takes 400 years to go from 100 to 50. It would take 400 years to go from 50 to 25 and so on. Now we only want to go 50 years. Oh, so we're barely going anywhere here. So anyway, in order to solve this, what we want to do is we want to write it as a exponential function and say y is, I'm starting at 100. What am I doing? I keep cutting it in half. What do you say we use a 1/2 then? Suppose I could use a 0.5 if I wanted to. And how often? Every 400 years. So remember where all the pieces go. Start at 100, keep multiplying by 1/2 every 400 years. The formula just writes itself almost. So if I want to plug in t equals 50, then I'll probably have to get out my calculator. So this is like a 0.5 raised to the 50 over 100. 50 over 400 is like 1/8. And then times 100. So I'm getting 91.7. So you'll still have 91.7 kilograms in 50 years. At least you lost some of it. You started at 100, you lost some. But it would take 400 years to go all the way down to 50, right? So that's what we expected. Something pretty close to 100, really. Cool. So I hope you kind of like those. I love these formulas. They're so easy. You just put them right together. Boom, boom, boom. You're done. Boom, 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 and you can use them. So getting back to the question, what's the difference between a geometric and a geometric growth and exponential growth? Geometric growth looks like this. You just keep taking steps, 40, 80, 160, 320. But with exponential growth, in fact, let me do it this way. Geometric growth looks like this, point, 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 point. Exponential growth looks like this. So geometric, you have to solve for the nth term or the n plus 1th term or the n plus 2th term. But exponential growth, you can solve anywhere in between as well. So this is called a, I want to say finite? Discrete, that's the word. This is a discrete, that's the word you'll hear. And this is called continuous. Continuous functions versus discrete functions. It's a word you'll probably see somewhere. Anyway, I think that's good. We're good. Exponential functions, they're cool. They're